books on my shelf, and they all share a common theme, and it's a very strong claim. And it's that gravity is universal. And to me, that means there's two interpretations for what universal could mean. So one possible application is that it means that gravity is applicable on the scale of the entire universe, both time and distance scales. The other interpretation of that, to me, is that it applies to all things. Gravity, when we account for it, will find its way into all physical phenomenon. The third option is that it's both. It's all of the above. And in this talk, I'm glad to tell you that it will be both. This will be both on the scale of the entire universe, and it will at least find its way into three different phenomena that we'll talk about. So I know that not everybody's a GR specialist in the building, so I'd like to give everybody a brief rundown of what do you need to know to understand this talk. First things first, we'll talk about what a metric tensor is, or what the metric is. What the scale factor is, that'll be denoted by this function of time, which is called R of t. And then Hubble's law and the Hubble parameter, which will be denoted by the letter H, capital letter H. And those are the three things that I think you need to understand in order to see how things change. Everything else I can introduce to you, along the way. So first things first, what is a metric tensor, or the metric? The metric effectively describes how distances are measured in space-time, okay? And it's usually represented by a 4x4 matrix, so that is an array of 4 rows and 4 columns of numbers. Generally, we use the metric to describe distances in space-time. This is the space-time interval, where mu and nu are both indices that run from 0 to 4. The convention that I'll be using is that 0 is referring to the time piece, and then 1 through 3 refer to the spatial pieces. Okay. In flat space-time, the metric will take this form. Okay, so the space-time interval where 0, this will be the 0 term. The space-time interval is denoted by c squared minus the spatial pieces. Okay. And this is a quantity that is invariant depending on Lorentz transformations. Okay, so the metric that we get from flat space-time is a positive one and then a bunch of minus ones on the diagonal. Okay, any deviation from that will indicate that we are no longer in flat space-time, we are in curved space-time. Okay, and that, for the purposes of this talk, means that there's gravity present. Okay, in spherical coordinates, so when we aren't talking about an x, y, and z, when we talk about a radius, how far away you are from the center, how far around you go, and then how far up or down you go. When we use spherical coordinates, this is the metric that we get in flat spacetime. So again, there's no gravity present in this case. The deviations so effectively where general relativity fits into this is general relativity is the framework that we use to solve for those metric components. And these are the Einstein field equations. It's a series, we use the Ricci tensor and the metric tensor, and the idea is that we're solving for the metric components to figure out how curved space-time gets. Okay. In the framework of cosmology, which is effectively the framework I'll be using today, the idea is that we assume two things about the universe. Is that on average, we assume that the universe is homogeneous, meaning that at any one point, on average, the universe is the same as any other point in space. And the universe is also isotropic, which means that any direction I look is as good as any other direction that I look in. And that's effectively what homogeneity and isotropy are. The consequence of that is that we get a different metric that's no longer flat. We get the Friedman-Lemaitre-Robertson-Walker metric. I will not say that title ever again. I will say FLRW if I ever need to reference that. And you'll notice the primary departure between flat space-time and curved space-time is the appearance of the scale factor, this R of t thing. I'll cover that in just a second. But that's our primary departure from flat space-time, is that we have moved, the space itself is something that is expanding. The neat demonstration that Dr. Ringwald was kind enough to lend me was the way to think about this is that I have a vacuum down here, and this on switch is down here. So what we see here when I was inflating this balloon was that each of these galaxies all appear to be receding from each other as the balloon was getting inflated. And it doesn't matter where you are in this, on this balloon, it doesn't matter where you look or where you are, all things seem to be getting farther away from you no matter what. Okay, that's my demonstration for what an expanding universe looks like. Okay. So our primary departure in Cartesian coordinates, so in terms of x, y's, and z's, you see that the scare factor, hopefully there's no scare factor, a scale factor appears in front of the x, y, and z coordinates. And you'll notice that time remains unchanged. The time that we use in cosmology is referred to as cosmic time or universal time. And that's the time that is measured by someone who is at rest with respect to the entire universe. And similarly, for spherical coordinates, so in terms of radii, polar angles, and azimuthal angles, we still see the scale factor is stretching things out. Okay. So one thing I forgot to mention is this is important for at the very end when I'm going to talk about plane wave propagation, and these two are important for when I talk about my first 2 points are going to be talking about electrostatics and the Klein-Gordon Coulomb problem. Okay, so that was my brief crash course on metrics. The next thing that I want to talk about is the scale factor itself. It's made a couple of appearances so far. The scale factor effectively describes how big the universe is at any given time. It describes the spatial separations between objects at any given time. It is constituted by basically the energy content of the universe. So sources of energy that I can think of off the top of my head are matter, radiation, dark matter, dark energy, and I will at no point make any claim to know what the ratio of those energy contributions are. So I'm just going to leave the scale factor unspecified entirely. Okay, I'm going to try to keep this sufficiently general. Okay, there's a big surprise at the end for at least figuring out what this might mean. Okay, and the last thing will be a brief history tour of what Hubble's law are and what the Hubble parameter is, where this capital letter H comes from in this context. So the Hubble's parameter is related to the scale factor, where this dot up top means it's the time rate of change of the scale factor. The Hubble parameter is defined as the time rate of change, as the ratio of the time rate of change divided by the scale factor itself. And the reason why that's important is because they might seem like they're the same thing. The scale factor is largely responsible for telling you how big the universe is, and the Hubble parameter describes the rate at which those things change. Okay, so that's a key difference. Here's my brief history lesson. Initially, the primary progenitor of general relativity, Albert Einstein, you may have heard of him before. Albert Einstein initially thought that the universe was entirely static, and he worked very hard to make sure that the universe did not change. And you can't really blame him, because when you look up at the night sky on a night-to-night basis, you really don't see a whole lot changing. So show the man some sympathy. Okay, it wasn't until the reason why that's controversial is because when he arrived at the Friedmann-Lemaitre-Robertson-Walker metric, when that was arrived at, it is inevitable that the universe seems to evolve. The equations that Einstein himself is responsible for deriving seem to indicate that no matter what you do, that as long as there's matter in the universe, there is evolution. And he worked very hard to resist that, but Edwin Hubble was likely the first person responsible for having direct observational evidence that there is evolution in the universe, that the universe is expanding. And this is where Hubble's law comes from. Hubble initially noted that the farther back you look, the more distant the objects appeared, that the faster they seemed to be receding from us, which is strange. We know gravity is an attractive force, so intuitively it would seem that at least if the universe is evolving, it might be slowing down or it should be coming back together. But indeed, the results that we see, especially from the next three guys on this list, are refined measurements of Hubble's measurements. We see closer and closer values to the Hubble parameter, which is what dictates the evolution of the universe. We see closer and closer to the values, plural, that matters, the values of the Hubble parameter that we measure today. Okay, more on this in a bit. Okay, so that's all the background that I'm thinking that we need. Okay, so using this metric, we are going to examine three different electrodynamic phenomena. First things first, like any good physics student, we have to take a stop at electrostatics, and we'll take a look how spherically symmetric charge distributions behave in an expanding universe. We'll use those results to examine how a Klein-Gordon Coulomb atom, or the Coulomb problem, is affected by cosmic expansion. And then once those two things have been covered, we're going to close the book on those things and we'll set them off to the side and we'll examine something completely different. We'll talk about plane wave propagation, electromagnetic plane wave propagation in an expanding universe. So let's dive in. Now, like any good scientist, before diving into any of this, I have questions of what I could expect. And my initial guesses are, we're making corrections to known physics. If anybody's read through Griffiths or Jackson, like this is all stuff that we know pretty well. So what sort of corrections are we to expect? Well, they're going to be both very small. I'm imagining that I'm not going to measure these things like if I just look at them. They're going to be virtually undetectable on human timescales. Okay, so during the course of my life, I'm not expecting the laws of physics to change much, if at all. And the signature, because our primary departure from flat space-time is the scale factor, I'm thinking that the scale factor or the Hubble parameter, but I'm, in not knowing the results in advance, I'm hoping that to see the scale factor make appearances in the corrections to known physics. So that's my initial guess. Okay. So our first stop is with electrostatics, and we want to take a ball of charge, and we want to know in a vacuum what is the electric field at some specified point. How strong is that electric field outside of that charge distribution? And I won't say physics 4B student, but I'll say any physics 107A student is almost certainly going to tell you that this is the expression that you get for this. The Q here represents the total charge. So that is the total charge contained by this ball. The R squared represents the distance away. So if my ball of charge is where my fist is, and my laser pointer is the point in question, I want to know the strength at this point. It's proportional to 1 over R squared. And that vector points in the radial direction. So it either points in if it's attracting, or if it points away if it's repulsive. The primary departure from this is we get an expression that looks similar. We still get constants on top. We still get R squared. We still have a radial dependence. But notice we have this sneaky little scale factor that makes an appearance in the electric field. Okay. I left this intentionally unspecified, and I will after this slide. But in order to get our known physics for today back, we say, okay, well, I know what the physics of today is, so I set the time equal to our present era of cosmic expansion, and I say, well, I know the electric field now, so this constant net equals our current era of cosmic expansion times Coulomb's constant times whatever charge that I'm looking at in question. And voila, we have a general expression for some ball of charge and the electric field outside of that in an expanding universe. Okay. And it's not tremendously difficult to get the electric potential, the electrostatic potential back. We take the radial derivative, well, we go backwards, okay? We take the gradient to get the electric field from the potential. So going backwards, we lose a factor of R in the denominator, and voila, we have our electrostatic potential. This is going to be important because we are going to use this in the Klein-Gordon Coulomb problem, where the potential that we're using here is the potential that we just found, okay? And the minus sign appears in here because the charge of the electron is a negative charge, so that's why that makes an appearance. The thing that I'm particularly interested in are, what are the energy, did I skip a slide? No, I did not. The thing that I'm most particularly interested in are the energy eigenvalues, because those are going to be the things that tell me the most about what's going on. So first things first, in flat space-time, the Klein-Gordon energy eigenvalues, we see mc squared makes an appearance, but we also see that the energy eigenvalues depend on the quantum numbers n, the principal quantum number, and the orbital quantum numbers L, and alpha being the fine structure constant. When we account for cosmic expansion in these calculations, it is a nightmare of an expression to get with many substitutions, so I tried to put everything up on the board. But we notice, here's our signature. We notice that the Hubble parameter itself makes an appearance in the energy eigenvalues. And here's the other curiosity. You'll notice that there is a real part here, so we see the regular Klein-Gordon equations with a very small correction next to it. But the other part that we get, you'll notice there's that funny letter I that appears. And that to me tells me that we get not just real, we get a real part here, we also get a complex eigenvalue. And what that means to me is at least one thing. One, or that means two things to me. One is that typically in quantum mechanics, we talk about the Hamiltonian or operators pertaining to measurable quantities being Hermitian. Hermitian operators guarantee that you get a real number for your energy, or for whatever measurement you're making. So the Hamiltonian is the thing that's responsible for energy. Our Hamiltonian clearly in an expanding universe can't be Hermitian anymore. And more importantly, what that means to me is that if my wave function is a stationary state, okay, where I have the time piece of my wave function depending on the energy, I have a real part over here, and all of a sudden I lose that factor of I that's in front, and I get some kind of decay that takes place. So my wave function is something that is going to decay over time. Okay, and my fun note, so if matter itself seems to decay over cosmic timescales, don't panic. I tried to put a little warning in here. Don't worry. This is something that is likely to take place over tens of billions of years. So you will not wake up tomorrow. You will likely be here tomorrow. Okay. The other thing to note is that this is an approximate solution. This is an approximate solution on the assumption that over atomic timescales, that the scale factor times the radial distance is something that's approximately constant. Okay, I'm going to, as promised, I'm going to close the book on that, so any questions that you have, keep those in your back pocket. The last stop that we're going to make on our tour of cosmic expansion's effect on electrodynamic phenomena is going to be on electromagnetic waves. So in flat space-time, we get a nice wave equation for both electric and magnetic fields, and they yield sinusoidal functions as their solution. Our electric field is some cosine where we have k as the wave vector that tells you what direction your wave is propagating in, and the frequency tells you how fast those oscillations take place. Okay. In curved spacetime, however, we get some wacky-looking results, and I don't say wacky just because I've changed notation. We get a couple of things here. So, one, we notice that our scale factor makes an appearance again, okay, and it only seems to make an appearance with the electric field, which is a curiosity that unfortunately I don't have any real answers to. But nonetheless, the scale factor makes an appearance. You'll also notice that, at least in the previous slide here, that I had, good old-fashioned time in my as my time derivative. You'll notice that I've changed notation here, where there's a Greek letter eta downstairs for our time derivative. And the reason why is because I have switched from using standard cosmic time to conformal time, where conformal time is effectively our neat trick that allows us to study electromagnetic wave propagation in an expanding universe where our light cones stay at 45-degree angles. So the speed of light doesn't depend on when you are. So that's my neat switch here. So we still get neat solutions, we still get sines and we still get cosines. I'm going to stick with cosines, and you'll see why in just a second. Okay. One thing that I'd like to add in here is this. Okay. Well, here's the other thing that I forgot to mention, was that the scale factor, there's a 1 over the scale factor that appears here. This is a nice consistency check to at least tell me that my results are somewhat meaningful. The scale factor in the denominator also made an appearance with the electrostatic field, so maybe we're onto something here. Now, there's another tensor I haven't talked about, but don't worry, I'm not going to flesh out every little detail about it. There's really two things about the energy momentum tensor that I care about. The energy momentum tensor is effectively a 4-dimensional pressures that we're talking about, so pressures in space and time. And the thing that I care about the most is the energy density. So that's when the indices over here are 0 and 0. And I want to know if I sum along the diagonal entries, do I still get a 0? Those are going to be things that are very important to me. A 0 trace of my energy momentum tensor tells me that photons are indeed massless. They don't carry any mass along with them. Well, the good news is, first things first, I get an energy density that appears to both the electric field, here's my electric field here, and my magnetic field components, they both decay, recalling that my electric field already contains a scale factor in the denominator. They both appear to decay with 1 over r to the 4th dependence. Okay? This is something that is commonly argued via symmetry arguments, using the geometrical optics approximation. I have made no such approximation. These are physical waves that we're talking about. So it's nice to see that we get those consistency checks with geometrical optics and physical optics. The next thing, I tried typing in these equations to these slides and they were so massive that it looked heinous, so I just copied and pasted this image straight out of my thesis. And indeed, we still get a massless energy, we still get massless photons. So if you are hoping to use physical optics to probe for massive photons, at least what I have to say is that you're likely to get not great results with that search. Okay, now I've done a lot of talking so far, and it seems like I've offered no solutions to real problems. We are today in a state of crisis. I don't know if I read the news, so I hope you do too. We are in a state of crisis, and it's not about budget cuts. We are not in a crisis about tariffs. No. We are in a crisis about cosmic expansion. So if you've read, I don't know how often you read the news, but a problem in cosmology today is referred to as the Hubble tension, and it has to do with the measured value that we have for the Hubble parameter. There are two primary schools that we get. There is what's referred to as the CMB, the Cosmic Microwave Background School of Measurements. And they tend to get measurements for the Hubble parameter around 65.5 kilometers per second per megaparsec. Meanwhile, the Cosmic Ladder School tends to get measurements that are much higher than that. And that might just seem like a neat discrepancy, but the issue seems to be that their error bars don't seem to overlap. And there is a statistically significant difference between those measurements. So what gives? Which one's the right value? Which one correctly describes the rate of expansion in the universe? Well, I have a solution, I think. If we have waves, okay, if we have wave propagation and we can do that in an expanding universe, ideally we can combine two waves to make beats. Now, for those of us that don't know what beats are, this is another neat demonstration that Dr. Ringwald was kind enough to offer. I have two waves that are approximately in tune. Okay, those to my ears sound like they're more or less in tune. Now, when I shorten the wavelength of one of these, or when I shorten the length of one of these, okay, listen to if you hear like a little whoa, 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 like a whoa, there we go. Do we hear that little woo, woo, woo? See a lot of nodding heads, that's a good sign, okay, good. So those are effectively the beats in time, okay? Because we have wave propagation, we also have spatial beats as well. This trigonometric identity is something that we can use to find what our spatial and temporal differences in beats are. Okay, so this is my drawing of what the combined wave would look like, and yes, this is absolutely the limit of my artistic abilities. But this is, so we get, we can get something that, look, we can measure the time separation between the physical beats, and we can measure the time difference between the envelope of that of the wave. We can also do that in space as well. The conditions that we end up getting for these expressions are listed here. But the neat trick here, so these are neat and things that are reasonably easy to measure. The issue is that I'm using conformal time still, which again, for all intents and purposes, is just a mathematical trick that we can use. So I want to know what the real gosh darn time is. I want to use good old-fashioned stopwatches and figure out what the time temporal separation is. Well, assuming that over the course of one wavelength, over one cycle of light, or one cycle, that these distances are small, I can use Taylor expansion to expand out my conformal time into cosmic time or local time based on the time that I receive these beats, okay? And I can solve for the Hubble parameter in my expressions, in my conditions that I have here, okay? Where the ratio of these two beats are, or the ratio of these beats are the same. And voila, using local measurements only, I am making a claim that if we're able to measure these beats, that in principle, we can directly measure the Hubble parameter, okay? This is something that is done with the wave nature of light. This is likely something that you cannot get using the physical or the geometrical optics approximation, okay? The other thing that I didn't write in here was that I'm not making any sort of claim to know how to measure this. I'm going to leave that to much more clever people than me. But I'm saying in principle, if we can measure these beats, then it is entirely possible to measure the Hubble parameter. The advantage of measuring the Hubble parameter here is that, recall, Hubble's law that I snuck into a slide in the past says that the speed at which these distant stellar objects are moving farther away from us is proportional to their separation, okay? Both of these things are both reasonably difficult because of how far away they are, and they can be a tremendous source of lack of precision. I would argue that it's easier to measure things locally and not have to probe the distant cosmos for answers to our questions. So at the very end of the day, okay, just to wrap some things up, that's about all I have for everybody. So in all of these phenomena that I've talked about today, decay seems to be a common feature of cosmic expansion. So electrostatic field strength decays, the energy eigenvalues, and the wave function all are things that seem to decay with time. If energy is something that is truly conserved, and these energy values that I've measured are things that decay, does the energy change forms, or do we need to possibly make modifications to our understanding of energy conservation? To reiterate a curiosity that I had was, if the strength of the electric field seems to be affected by the cosmic expansion, the scale factor, why isn't the magnetic field? Does this say anything at all, if anything, about the nature of magnetism at all? And my last point is, these are all very small corrections. Are we able to detect these? Are these things that we can measure? Physics is, after all, a science, and I can do all the calculations I want on a whiteboard or with my friends in my spare time, but it doesn't mean anything unless there is experimental credence that is lent to these ideas. So I'm hoping someday that maybe we can detect any of these and have further evidence of cosmic expansion. But that's all I have for everybody. Those are questions that I have. Are there any questions that you have?
First of all, that was a fabulous talk. Thank you, Phil.
Thank you.
Sincerely, yeah, more than delivered on your promises, so I was very excited to hear this talk.
Sweet.
I'm super curious about your second bullet on the previous slide, which you yourself you indicated is an open question. I wondered about that when I was listening to you explain the electric part and the magnetic part. Why would there be an asymmetry in the two waves? Like if we go back earlier in your set of slides, and you have the two wave equations in flat space-time, and then you go over into curved space-time with the FLRW metric. Since the two wave equations are completely mathematically identical, what is the reason that the electric field wave equation ends up with the scale factor? You know what I'm talking about earlier?
Yeah, no, I know what you're talking about. So my answer off the top of my head is that we're using the tensor form. Oh, I don't have any of that in my slide. We're using the electromagnetic field tensor to calculate all of these.
Yes.
When you do the wave equation, especially using the Bianchi identity in curved spacetime, you end up getting two completely different expressions when you change the indices. So if 0 and I, 0 and a spatial index, and then I and J, you get completely different expressions. I'm happy to share those with you. Yeah.
Sure. Can you go back to the wave equations you had in flat space-time?
Yeah.
So
in flat
just to really
space-time.
elucidate the contrast.
Yeah.
Yeah,
so
there.
Flat space time.
Like there, naively, you would think that those two wave equations should get modified exactly the same, right?
Yeah. So a curiosity. This was a quick and dirty. Literally did on a napkin calculation.
Okay.
I did like Gauss's law for magnetism, and I found that the scale factor also doesn't make an appearance there.
Okay. But in the next slide over,
On the
right
magnetic,
there.
just on the magnetic field part, yeah.
Yeah, right there.
Yeah.
We lost the symmetry of the two equations right there.
Yep.
Okay, so maybe you can just show me later when the gory details, because off the top of my head, I cannot see why that symmetry would be broken.
But, okay, so I'll say something good and something bad for Phil.
Great. Sign me up.
So the thing is, one thing is, look, the Friedman-Robertson-Walker thing is all about time, right? It picks out
Yeah.
time, not space. And basically the electric field is the space-time component of the tensor, whereas
Right.
the magnetic thing is purely spatial.
Space.
Yeah.
Yes.
So that's the good.
Yeah.
And so then the other thing is though, but under Lorentz transformations, you have invariance, right? And you can move to different frames where you can change, I mean, there's some restrictions, but you can change electric fields to magnetic fields and vice versa.
Mm.
So that would seem weird then, that like, the electric field has this extra thing, but if you do a Lorentz transformation, now something that was an electric field or partially electric field in one frame becomes a magnetic field in the other frame, so does it lose that factor? That would seem, right?
Well, you lose
see what I'm saying?
Lorentz symmetry, but should Lorentz symmetry necessarily be obeyed in curved space-time
Locally, right? It has to be.
locally?
Anyway, so I don't know the answer, but so
I also
the
don't know
one
the answer.
one thing is like, again, the electric field is the space-time component of the tensor, and the Friedman-Robertson-Walker is it focuses on the time, not the space. So maybe that's why.
Possibly.
Rachel?
Yeah, you mentioned at the very beginning, you say something about from that invariance, you say the time is absolute, and then something inertia or rest, but if the universe is expanding, where is that inertia placed?
I don't know the answer off the top of my head. My best guess to that is the choice of coordinates that you use in the Friedman-Robertson-Walker metric are just referred to as co-moving coordinates. So the choice of coordinates says that the physical objects, their separation is expanding, but their physical distance changes. Hold on. There's a better way to say all of that. The coordinates are the things that are changing, and not necessarily just the physical distances. So it's your grid is your balloon is the thing that's expanding, and not the objects that are placed on it. I don't know if that answers your question.
And another thing is you're writing the Coulomb force with a scaling factor. Isn't that supposed to be an R square, capital R square in the denominator?
So I got that question before. I would suspect that would also be the case. I've done the calculation 1,000 times and I can't get any. In the Coulomb force, I have done it 1,000 times and it's just a single R that's in the bottom. I find that peculiar as well.
Is it because there's an R squared in the metric? So in the metric, it comes in as an R squared multiplying the spatial part, right?
Yeah, go back to the metric.
Yeah,
Yeah.
go back to the metric. Yeah, there. But still, the R squared and the dx squared are of course the same order, so they ought to vary together.
Yeah. It depends on whether or not you're using the field tensor upstairs or downstairs. If you end up doing the electric field for the, let's see, for the metric upstairs, then you get an r to the third that's on the bottom. So in either case, you still don't get an exact matching up of the term. I also find that to be a curiosity, and I don't. So I was at the Pacific Coast Gravity meeting last week, and one of the judges reached out to me and offered a solution, and I haven't taken the time to really look into it.
Was there any approximation made when you did the calculation, or is it exact?
This is exact.
Well,
The only-
metric is fine, but I meant when you go to the Coulomb field, did you, because I noticed you mentioned about Taylor expanding and things of that nature.
Mhm.
Was there any kind of approximation taking place there?
For the Coulomb force, no.
Got it,
Yeah. For the Coulomb force and the wave equations themselves,
Yeah.
those are exact.
got it.
Okay.
Nathan mentioned on your next to last slide, the middle point about yeah, amplitude of the magnetic field of electromagnetic wave, unaffected by cosmic expansion. A friend of mine at New Mexico State, Chris Churchill, has looked into this problem in a fair amount of detail, although maybe not enough. He's looked at the light of distant quasars and measured the relative wavelengths of different spectral lines and different elements to see if they shift over time. In other words, is the fine structure constant changing over time? So that might be an avenue for looking into. Also, could you go up a slide? Yeah, okay. This would be an independent measurement of the Hubble parameter, would be a very big deal indeed, especially if you could do it with local measurements. There are various, the LIGO project, for example, can measure astonishingly tiny amplitudes due to gravitational waves. And a Michelson interferometer, several kilometers with each end, kilometers long, capable of measuring tiny shifts. If you could generate some real numbers with this, and publish them, a lot of LIGO people and a lot of astronomers would be very interested indeed. Where do you intend to publish this?
It's a work in progress at the moment. I'm working on a manuscript.
Okay.
And that's about all I've got.
Well, I might suggest one of the astronomy journals, either the Astrophysical Journal or New Astronomy. The Astrophysical Observatory is, of course, the top of the line, the most prestigious one. You also have to pay to publish in it. They have publication charges.
Mm-hmm.
If you can't raise the money to do it, send it off to New Astronomy, because after I looked at that, they have a really nice impact factor these days. So even though it's a free journal, it's people read it.
So AppJ isn't free, but New Astronomy is.
New Astronomy is free, yes.
Yeah, I mean, I don't know much about astronomy journals, but I know AppJ is kind of the top tier besides AppJ Letters.
Yeah.
The library actually has funds for, limited funds for if you publish in like a journal that charges, they'll pay for
Yeah.
the author, the page charges. They have, it's like $10,000 or $5,000, so once it runs out, then it's gone, but so.
Yeah.
And I know someone who's on the library committee.
Oh,
What
sweet.
was his-
Gerardo.
Oh, sweet.
The thing is, in biology and chemistry, the top tier journals are free, and the second tier journals you have to pay. In astronomy, it's the reverse. I've never been able to convince a dean, who is inevitably a biologist or chemist, that this is true. But nevertheless, New Astronomy is free, and it's a darn good journal. It has a very high impact factor. So definitely, again, see if you can come up with even if there are only order of magnitude estimates. This is potentially of quite a bit of interest.
I think so too.
Yeah.
Yeah, Paul.
So, I've had this question in my mind for a while, and it kind of came up that what Einstein was trying to do with gravity was, he was trying to figure this out, but maintain a steady state universe. Is that correct?
I believe so, yeah.
So, but I mean, Einstein knew about entropy at that. I mean, I'm sure, I've always wondered how can someone advocate or you know, like, want a steady state universe. Did he have something in mind for like a constant supply of low entropy somehow, or what was he thinking about that? Or does it, I mean, I know it's not related to you.
I don't know off the top of my head, but at least my understanding so in the Einstein field equations, some few decades ago, the cosmological constant term was largely introduced to help keep the universe static. I think that's so the capital letter lambda was more or less introduced because it's consistent.
Well, that's just keeping
yeah.
everything where it is, right? But
Yeah.
did he still think everything was going to run down? It was just going to run down in place?
I offer no glimpses into Albert Einstein's mind. I don't know is the answer. to
Well,
that
if I can
question.
make a quick comment, lambda is just holding the universe size static. It's
Right.
not telling us anything about entropy change.
So it's still
Right.
going to run down. It's just like
Yeah,
it's
from
gonna
an
run
entropy
down.
point of view, that equation, unless anyone can comment beyond, is only telling us that if you fine tune lambda, then the fact that T mu nu is going to cause everything to collapse, lambda is going to make everything expand. You can hold it static as far as the volume or space-time volume of it goes. It's not telling us anything about energy distribution specifically, or entropy, or any of those other like thermodynamical type considerations. You just want to hold it like static, size-wise. Yeah.
Yeah, the idea that the universe could be expanding, that space could be expanding, space and time itself could be expanding, is frankly an idea too fantastic even for Einstein. Although in hindsight, and of course hindsight can be so cruel, it's actually quite a natural thing. Gravity always attracts. So therefore a static universe could not exist. It would either collapse or have to be expanding. But that of course is with the benefit of hindsight. So, and the thing is, in the constant, when doing the derivation for this, lambda is a constant of integration that really should be there, and there is no reason why it should have any particular value, such as 0. So Einstein sees that and says, oh, that must be what causes the universe to be static. 13 years later, Edwin Hubble could actually show him, actually, in fact, the universe is expanding, and Einstein called it the greatest blunder he ever made, the greatest scientific blunder he ever made. The thing is, though, Fred Hoyle and Tommy Gold and Herman Bondi still hated the idea that the universe could be expanding, because if you, again, Edwin Hubble showed the universe is expanding, which would imply that in the distant past it was a lot denser. And since it'll still follow the ideal gas law for any gas, that you would have an initial hot, dense state, widely referred to today as the Big Bang. And of course, the question to ask about that is, well, what happened before that? And the short answer is we don't know. But nevertheless, Fred Hoyle, Herman Bondi, and Tommy Gold said, listen, anytime in any physical theory you have a singularity appearing, that's usually disaster, especially if it's about the origin of the universe. So, therefore, they came up with the steady state theory cosmology, that the universe is expanding, but constantly coming into creation all at once. And you say, doesn't that violate the first law of thermodynamics? The answer is no more than the Big Bang. Only in the Big Bang, all the energy in the universe comes into existence all at once. So steady state, it would come in. Steady state predicts that the universe should not be evolving. That should always be the same over cosmic time. We now know for sure that's wrong. We see galaxies evolving. We see galaxy clusters clustering. A young Earth creationist in PSI 21 asked me, if the universe is expanding, how can galaxies cluster? And I told them, cause the rich get richer and the poor get poorer.
Probably like that answer.
Yeah, usually I'm not that good, but that was a good one though. Another thing is steady state, cosmology doesn't predict the existence of the cosmic background radiation, the leftover waste heat from the Big Bang, which Penzias and Wilson would discover in 1964. And they got the Nobel Prize for it, and Bob Dickey didn't. So, yeah, no, this is, Philip, you really ought to write this up and publish it. This is a good one.
It's awesome. Can I ask one more technical question?
Sure.
Going back over to the wave equations again, if you don't mind?
Yeah,
I
totally.
was just curious, right, yeah, there are,
Here?
or, yeah, there's fine.
Yeah.
So I know that like, when you go to curved space-time, you basically have a box operator acting on each of those fields, right? And I do remember that, like, if I recall correctly, when you apply the box operator in curved space-time, I think you pick up an extra term that has like a Ricci scalar, I believe.
If you do that with the, the way that we did this calculation was using the Bianchi identity, but because the lower indices and the Christoffel symbols are symmetric, and because the field tensor is antisymmetric, you
Yes.
actually get right back to the flat spacetime version, which ended up being the easiest avenue of solving this.
Okay, so
Yeah.
I guess maybe that would be another like interesting technical conversation later because
Yeah, we can have a
I
whiteboard.
would think, yeah, because I would think if I recall correctly, I've looked at a lot of this also, and I remember like that box operator, even though you're right, like if you apply the covariant derivative on the E&M strength tensor, you do lose a term because of the anti-symmetry of the strength tensor and the symmetry of the Christoffel symbol.
Yep.
But when you go to take the second derivative, so you act the covariant derivative on the prior evaluated derivative, then you pick up a term in the end that ultimately ends up being a Ricci scalar term. It's actually in the book by Brill and Davies, I believe. Doug's brought that book to my attention
Yeah.
before, right?
Brill and
Yeah, the
Davies.
Brill and Davies. So where they look at it's I think quantum field theory and curved spacetime, I think is
Yeah.
the book.
Yeah.
And so I took note of that before because the wave equation picks up that extra Ricci scalar, and for the FLRW metric, the Ricci scalar is non-zero. So I would have thought that you'd pick up another term that would be present in the wave equation that appears to be. So what I'm really ultimately getting at is how did you introduce curved spacetime just by introducing the metric to the coordinates, or also changing your derivatives to covariant derivatives? Yeah, when you got there.
Yeah, okay. My answer to that would be that there was a lot of chain rule substitutions that include the metric, and then getting everything in terms of covariant form, so all the indices are downstairs. That introduced the metric into the wave equation.
So you didn't take your del squared, for instance, and turn it into a del nu with g mu nu, and then the Christoffel symbols come in and it turns into a big gory mess, and then clean it all up, sort of thing?
Okay, I'm having a hard time visualizing that. Yes. I think I need a whiteboard.
Well, yeah, we need a board.
Yeah.
So yeah, I'd love to look at this with you because I'm really curious about how the whole like the
Yeah,
details
no,
pan out.
it's metric, covariant derivatives, the whole legal thing.
The whole deal,
big
because you
gory
worked with them
message.
on this, I guess,
Yeah.
right?
Yeah.
It's all in there.
So it's all in there,
It's
and
all
it
in
cleans
there.
up to just that.
Yeah.
Yep.
Wow.
Yeah.
Okay.
So the Ricci tensor appears in there, and it comes in there because you have second order derivatives in time,
Uh-huh.
and the Ricci tensor appears as second order derivatives for the scale factor. So it is in there.
Oh, and then the Ricci scalar does not appear?
No, because the wave equation, for example, if you look at the vector potential, has the Ricci tensor by itself,
Gotcha.
right?
Gotcha.
But all that appears in there.
It's all in there.
Yeah.
That's crazy. It cleans up that much.
Yep.
Yeah.
Okay.
Yeah.
Thank you.
We spent about a month making bajillion mistakes over and over again.
Oh, I don't doubt that. There's
Once
so
we
much that
got it-
goes into what you have right there
Yeah,
that
once-
probably, yeah.
Once that happened, we said, all right, let's make sure this happens again. And, we got it right 3 times in a row, so we
Nice.
checked it off. Yeah, I'm happy to share that with you at some point.
Thank you.
A bajillion, is that a technical term?
That is a technical term, yeah.
Yes.
Yeah, I'm shocked you haven't seen that.
Yeah. It's what a grad student experiences
10 to the
when they're
bazillion.
doing
Yeah.
a thesis.
Everything seems like it happens a million times when you make the same
Exactly.
mistake over and over again. Yeah.
I have one more question.
Yeah.
We expect now, because it seemed like you change fundamental constants, no? I mean, you change the Coulomb law. Are you expecting any other fundamental, like Planck constant to change in expanding?
That is, yeah, so one of the ways that I think, I don't know, to answer your question, I don't know how to answer that question, but that would certainly lend, one of the things that I talked about in my thesis as an interpretation of the scale factor being introduced was Dirac postulated that maybe cosmology is an avenue for exploring how expanding universes actually have dynamical constants.
Okay.
So that's a possible interpretation.
And it's interesting that the scaling factor doesn't appear in the B field, which also means we don't have magnetic charge.
Yeah. Yeah, agreed.
Any other questions? Now let's hear again. We have one more talk after the break, so no talking in the break.
Sweet. Let's get some words.
Nice talk, Phil. I really appreciate when you bring demos too, so